Right, PlasMa currently simulates 3 different computer systems. The internal MCU, an Atmega 2560, simulates peripheral hardware and emulates one of 3 CPUs via a microcode which can be loaded by the operator. The operator or user can then write and execute programs using the machine code instructions, or opcodes, for the chosen CPU. Our previous video showed a 4th system written in one of these machine codes, called PleX, and this worked okay, albeit slowly, but it raised an intriguing question: could a new microcode be written to emulate a 4th CPU directly? Well, it seems the answer is yes, so the new microcode will be available in PlasMa version 6, and that's the topic for this video. Now, just a word of warning, there's a lot of low-level detail which may be old hat to 4th experts, as it includes examples showing how 4th works. This is mainly for my benefit as a 4th novice, but hopefully it might help other newcomers to appreciate Chuck Moore's genius. I can highly recommend Chuck's article, or unpublished book as he describes it, called Programming a Problem-Oriented Language. It's a fascinating insight into the thinking behind 4th. And if you're in a rush, a simple demo is first, and then the details. So, assuming PlasMa is powered up, you load the new microcode in the usual way. You set 4 on these switches. What were the chances? Set FMP, reset the CPU, and run. And microcode 4 is loaded. You then reset FMP, set the CPU's program counter to the cold start address, and run. The emulation uses the screen as a simple teletype, with old school green phosphor of course, and output is also echoed to the printer if it's online. The 4th is now listening for input from the built-in keypad for very simple tests, the QWERTY keyboard, or the paper tape reader. I'll use the keyboard for now. I can enter expressions like 2, 3, plus, dot, which adds the 2 numbers and prints the result. Or I can define new words. I'll use similar ones to the PleX video. This one prints a new line, or carriage return, called CR, and it just passes the ASCII code 10 to the built-in emit word. So if I enter CR, we get a new line. Here's another for printing the word no, called pno, which passes the ASCII codes for N and O to emit, and then invokes the CR word just created. It's the name of the word. 78 emit, which is the N. 79 emit, which is the O. Carriage return, end of definition. So, pno prints no. And at the risk of heresy, if you don't like the cryptic names for the built-in words, just redefine them. You could change the colon word, say, to define, and you could redefine the dot word to print. Define, print, that's the dot. So now you can enter 2, 3, plus, print, and it does the same as before. Okay, all very basic, but let's go deeper and see what PlasMa can bring to the party. With conventional CPUs, the control switches allow you to run CPU opcodes at full or variable speeds. That's all these up here. You can also step through them one at a time, and they also allow you to load values or set breakpoints on main memory contents and CPU registers. And these lights display all these items in real time. I wanted to keep as much of this as possible for 4th, so its CPU operates on 4th words, which are its fundamental building blocks as opposed to opcodes, and displays registers or other items relevant to fourth. Now, I did mention the idea in a fourth presentation video and asked for suggestions on what to display, but there were no replies. So the following is what I've found useful so far as a fourth novice. And speaking of which, apologies in advance for any incorrect terminology or statements. The dictionary and buffers are held in main store, as shown on this layout map. Main store is 64 kilowords, the same as PleX, and you can inspect or alter the contents using these memory switches as normal. Only a 16-bit value can be displayed at any one time, but the PlasMa Sim simulator, which is built using the same code as the real machine, has been enhanced to display 8 consecutive words in character format. The program counter lights display the address of each fourth word about to be executed, or more accurately, it displays its code field address. The interpreter pointer, mentioned in many fourth guides, is usually the same value, but it's not displayed directly to avoid confusion. This was one of my many head-scratching moments, which I'll explain later. The instruction register lights, that's these, display code field address contents, which are typically also code field addresses for other words. And by the way, if ever you need a workout for those little grey cells, writing pointer handling code for a fourth engine certainly does the job. The simulator can be more instructive here than the real machine, as it annotates the code word value with the name of the word, along with decimal decodes for other items. Now, there are no such luxuries on the real machine. It's much more fun, but you just have to get down and dirty with binary and hex. The parameter stack is a crucial part of fourth and is used to pass parameters between words. The bottom left row is the stack pointer, SP, and the 7 rows above it are the top 7 items on the stack. The top row is always the item most recently added. So an empty stack looks like this, and it's located in memory such that SP starts off at an easy to read hex value of 40. The built-in interpreter's rule is that if a word is not in the dictionary but is a valid number, it will be pushed onto the stack. So if I enter 2, there it is. The stack grows downwards in memory, so the pointer is now hex 3F. Enter 3, the entries are pushed down the stack, and SP is now 3E. The CPU flags are also repurposed. The first one is set if the system is waiting for input, which is what it's doing now, and the second one summarizes the state of the parameter stack. If it's lit, like now, the stack is in use. If I enter drop and drop, the light turns off to show the stack is now empty. Now, you could obviously deduce that from the stack pointer, but the flag is easy to see at a glance. So here's the addition example from before, but I'll enter one word at a time. 2 goes on the stack, 3 goes on the stack, plus pops the 2 numbers, adds them together and pushes the result, and dot pops the result and prints it. Now, another crucial item is the return stack, which is used to save and restore the interpreter pointer when one word calls another. The right hand lights display this, with the stack pointer RSP on the bottom row, but this time only the top 5 entries are displayed. And as you probably guessed, the third flag shows its state, where off means empty. Now, you may have heard some odd clicks or pops earlier when I was entering words. Now, these were not audio glitches, they were sounds from the jump click speaker, which is normally triggered by CPU jump instructions to give an audible sense of what the program is doing. I've tied this to the primitive branch words, so the sound you heard was the branch in the outer interpreter as it looped back to listen for the next word. Here's a noisier example with a temporary built-in word called test, which just decrements whatever value is on stack and loops till it reaches 0. I'll put 1000 on the stack, then test. Okay, moving on to the built-in dictionary. The earlier PleX program was based on Jones-Forth, and that used assembler macros to generate the dictionary structure at assembly time. And PlasMa's firmware and microcodes are all written in C, but I find its macro processor very unintuitive at times, particularly with string handling. So I used normal C code to build the structure. The code is enabled or disabled with a compiler switch, so you just set the switch, compile and run, and that generates an include file in the C language like this, complete with whatever comments and annotations you want to make it easy to follow. You then reset the compiler switch, recompile, and this data structure is now included in the main code. You could probably automate this even further, but this is fine for me. The structure is copied from PlasMa's MCU into main store at startup. Now, there are many variations for the dictionary layout, all with different pros and cons, so this is just PlasMa's version, loosely based on Jones-Forth and using similar word names. Here's the definition for swap. The first item is the address of the previous entry, so in this case hex 123 points to the previous word called drop, and its link, hex 11b, points to interpret, and so on. And a 0 link means there are no more entries. So these links are a means of scanning through the dictionary backwards, which allows new words added at the end to override old words if they have the same name. The next item contains two flag bits called immediate and hidden, which are 0 in this case, and the length of the word name in characters. Swap is 4 characters, so this is 4. This one, interpret, is 9 characters, and so on. Next come the ASCII codes for the name itself, SWAP, and then the tricky part, the code field, which is a list of operations or code words which define what the word actually does. There's only one in this case, but this one, TDFA, has 4. Now, just to clarify what the lights show, if TDFA is about to be executed, the program counter would show 24F, and the instruction register would show the contents 0. The contents could be addresses of further words, similar to conventional functions calling other functions, or they could be primitive words, which are the ones which do the real work by controlling the underlying CPU. The contents might not even be word addresses. Their meaning depends entirely on the logic processing the list at that time. In other words, the word being executed controls both what the word is defined to do and the control flow for the whole system. There's no global overseer. And it's this ingenuity which allows Forth to be far more powerful than you first think. I'll show an example later. Now, on software Forth systems, like the PleX example, primitive words are actual machine code. But in this case, there is no machine code, so they directly control the underlying hardware CPU. Of course, PlasMa isn't that clever, so this is the part emulated using the A Minor MCU, if that makes sense. The flags and length values only need a byte for storage, and Jones-Forth allocates just that. But I chose to use a 16-bit word where the MS byte is always 0, and this gives a way of extracting the name of the word from its code field address. You can just backtrack until you hit the 0, although I'm not sure if this is useful just yet. Primitive words like these use an index to a code table. The dictionary is located in main store, starting at an address outside the range of the table, so the interpreter can easily distinguish between a dictionary address and a code index. Now, this is slower, but simpler for this first attempt. There was no point getting obsessed with speed until I knew it would work. So this entry, 4, is an index to the primitive functions table defined here, also auto-generated. And currently the table lives inside PlasMa's MCU as opposed to main store, and the contents are pointers to code functions in C. A later experiment is to store the code pointers directly in the dictionary. And as mentioned earlier, it's these code functions which emulate the hardware CPU. Now, new words can be added to main store just after the end of the dictionary, and this address is held in a variable called here, whose address is made public to the fourth user via a built-in word, also called here, if that's not too confusing. Here is here, and its initial value hex 2EF, which matches the next free address after the end of the built-in dictionary 2EE. Its value is displayed on this row of lights. So if I reload the microcode to reset the dictionary, it shows 2EF as expected. The next row of lights are the value of a similar variable called latest, which is the address of the last word added to the dictionary. The lights show 2E2, and the dictionary map file confirms it's the last definition called test. Now, both of these values grow as new entries are added, so are handy progress indicators if bulk input arrives from the paper tape reader. I'll show this later. The accumulator lights are currently unused, so I think that's covered all the lights. Now for the watching paint dry bit, I'm going to step through some words to show how they work. Now I found this very instructive, so it may be useful to others. If not, you can always fast forward. We've just initialized the fourth machine, and the pointer has been reset to 2B7, so we're at the first item in the quick definition, which is the cold start routine. Its job is to reset or clear the return stack, which is over here, and then keep calling the outer interpreter in a permanent loop. Now, both stacks are currently empty, and the waiting for input flag is off. Now, clearing the return stack is obviously pointless at the moment as we've just initialized it, but the quit word can be called later by the user, in which case the stack may not be empty. We'll just watch it go through the motions anyway. The first item's contents are 2C, which is the primitive index for the word called R0, and this will push the startup value of the return stack pointer onto the parameter stack. Tick. And hex 80 is now on top of the parameter stack. Now this shows how words also control their own destiny, as mentioned earlier. The R0 word, like most primitive words, has incremented the pointer to the next item in the list. So we're about to obey function 34, RSP store. Now this takes the value from the parameter stack and stores it into RSP, the return stack pointer. And this is also an example of how values are typically passed from one fourth word to another, similar to parameters in conventional function calls. So step. Right, no visible change on the return stack as expected, but the parameter stack is now empty. The pointer has incremented again, and we're now about to obey function 2, the interpret word. So watch the input flag. Step. The flag is lit, so the interpreter is now listening for input, or more specifically a fourth word, which is defined as a string of characters delimited by white space. I'll start the CPU running, so I can type 1024 space test, but I'll stop it before pressing enter, as I want to single step from then on. I can now press enter, and that key code will sit waiting in PlasMa's keyboard buffer, ready to be picked up at the next keyboard read request. The interpret routine will transfer characters from its input buffer into a word buffer, and this is held in main store at address 0. So if we set the memory switches to 0, we'll see the word arriving. The buffer is empty at the moment. I won't stop at every step, otherwise we'll all be asleep, but I'll just highlight a few for interest. Step, 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 step. Right, the first word, 1024, has now been transferred to the word buffer. And if you know your ASCII codes, you'll recognise these: 31, 30, and the next address, 32, 34. The step. The interpret routine has found that 1024 is not a word in the dictionary, but is a valid number, so it's pushed the value onto the stack. Hex 400 is 1024. We're about to obey function 46, which is a branch, so it will jump back to interpret and wait for the next word, and you should hear a click. Okay, a few more steps. The second word, test, has now been transferred to the word buffer. Hex codes 54, 45, 53, 54. We're still inside the interpret routine at 2B9, and it's about to check the dictionary again. Step. This time it found the word, and it's extracted the address of test's code field, its first code word or operation, at 2E6. This is shown here, along with its contents, function 0. Now we're still inside the interpret routine, so the instruction pointer is still 2B9. And this is why I display the code field address instead. It's more instructive to see what's about to be obeyed. And processing will continue at 2E6, but IP cannot be set to that value yet without saving it first, otherwise test won't know where to return after it's finished. The trick is to define words like test with their list of operations bracketed by two extra words, one to save IP and the other to restore it. In Jones 4th, these are called do call and exit. Okay, we're about to obey the first operation in test, function 0, which is the do call word, so keep an eye on the return stack. The do call has saved the old IP value and incremented the new value to 2E7, so we're about to obey the second operation, function B, and this is the primitive word called 1 minus or decrement, fourth speak for decrement the top item on stack. Step. The value has been decremented. Decimal 1023 is hex 3FF, and we're about to obey function 5, the dupe word, fourth speak for duplicate top of stack. Step. And there's the duplicate value. We needed to make a copy as the Z branch word up next pops the item from stack in order to test it. Step, step, step. Right, we've now looped back and decremented again, so 3FE is on the stack, which is 1022. Okay, you'll be relieved to hear I'm not going any further, but what if you wanted to check what happens when it reaches 0? Well, you could use PlasMa's breakpoint feature to set a breakpoint after the loop, say at the drop word here. Set to ED on the switches. You can see I've done this already. Turn on breakpoints. That's this light here. And run. We've got a break match, and we've stopped at 2ED. The stack holds the value 0, and you can see why the flag is useful here, as it says the stack is still in use, even though it looks empty at first glance. Right, we're about to obey function 3, the drop word. Step. Drop has done its thing, and the stack is now definitely empty. We're about to obey function 1, the exit word, which is the opposite of do call, and restores the flow of control. So keep an eye on the return stack and IP. Step. So this has been reloaded from the return stack and incremented. The return stack is empty and we're back in the outer interpreter loop at 2BA. I'll turn off breakpoints, and just for interest, here's test again running at slow speed with the variable clock. You can adjust the actual speed with this knob here. It's set quite slow at the moment. I'll put in 10 test, enter, and you'll see the stack counting down slowly with the duplicate, the code field address ticking through, and we're done, back waiting for input, back to full speed. Now I just mentioned the fourth flag light here, which displays the system state. Off means normal execute mode, which is what we're in now, and on means compile mode. Now, these modes confuse me at first, but it all starts to make sense when you can actually see the interpreter switching in and out of compile mode as it builds new entries. Here's a redefinition of the CR word from earlier. I'll enter it a word at a time so you can watch the lights. Start with colon, the define word. The colon routine waits for input, that's this light, and it's waiting for the name of the new word. So I'll type that in, I'm going to call it CR. And the word is now in the word buffer. We have a 43 and a 52, which is CNR. And it has enough information to start building a new definition header at the end of the dictionary. We can inspect the entries so far. Latest has been updated to the start of this word, 2EF. So let's set 2EF on the switches. And you can see the link value 2E2. This was the previous value of latest, which pointed to test. The next entry, 2F0, is 22, which is the word length of 2 and one of the flags mentioned earlier. And the top 3 bits of the byte are reserved for these, and this is the hidden flag. It's quite handy to see things in binary sometimes. Now this flag prevents subsequent lookups from finding this new word prematurely as it's incomplete. The next item, 2F1, is the word name, CR, and finally 2F2 holds the first item in the code field area, in this case function 0, the do-call word, which as we've seen will preserve IP when CR is used in future. The value of here is set to the free area after this header, 2F3. Okay, now the header is complete. The colon routine has switched the system into compile mode, if you spotted this, and returned to the interpret routine, which is 2B9. So instead of executing subsequent words, it will compile or convert them as necessary and append them to the code field area after do call. So let's enter the words now which form the definition of CR. 10, emit. Now you'd think it would just plant the value 10 and then the address of emit. But if a simple 10 was planted, the normal processing code for executing CR later will misinterpret it as a word address or a code index. To get around this, the interpret routine first plants the address of an extra word, which, when executed later, will take control over the dictionary processing and treat the item following it as a number, which is to be pushed onto stack, just like entering a number interactively like we did at the start. This extra word is called lit in Jonesforth for literal. So if we look at the new items planted, at 2F3 we've got function 21, which is the lit word, and 2F4 is the decimal 10. And finally we get back to normality at 2F5, which is 231, which is the address of emit. And finally the semicolon word ends the definition by planting the address for exit, which will restore IP when executed. And it switches the system back to normal execute mode. So watch the flag, semicolon, enter. And we can see 2F6 is now function 1, the exit word, and the value of here is now 2F7, which is the next free address for anyone else to use. Okay, let's load some more words from tape. Here's the current list of words. By the way, I was planning on cutting this down once it's all working, in keeping with Chuck's philosophy of only defining the words you need for a particular application, instead of predefining zillions of words you may never use. But that's something for later. Now, this paper tape has a few word definitions from Jonesforth, so I'll just show it loading. It's on now. You can see here and latest gradually creeping up, and the compile flag, and maybe some stack activity. Now, the slow speed may be due to PlasMa's tape reader running at 100 characters a second, which is intentional as PlasMa simulates that old school era. But I'll investigate performance later when I add system calls to access the mag tape and disk peripherals. These are faster block-based devices, so should be ideal for fourths, blocks or screens. Okay, the reader's reached the end of tape and turned off, and we can see more words have been added. Right, we now have flow control words like if, then, while and repeat. So let's try a couple from the previous PleX video. Now this one checks if the value on stack is greater than 9. So, colon, query greater than 9, name of the word. We want to compare the value with 9, and if it is greater than, we print yes, else we print no. And that ends the if statement. So if I put 4 on the stack and obey this word, query greater than 9, the answer is no. If I put 10 on the stack, the answer is yes. And finally, a simple loop, this one called .cd, prints a countdown from the start value on stack. Define .cd, begin, loop, 0 greater while, this is still very unnatural to me, but I'll persevere. Right, I hope I got that right. Let's do 9.cd. Amazing. Okay, that's it. Phew. Now, this was quite a roller coaster ride, much more frustrating than the software PleX version, which was a port from Jonesforth, so did not require every part to be fully understood. But it was great fun, especially now there's a happy ending. I've learned a lot more than I did before, even though I would still struggle to write anything of worth in Forth. But as the dying protons all sing at the end of the universe in my long-forgotten album, A Minor Excursion, it's not the end that matters at all, it's the journey. And on that musical note, thanks for watching.